So in this session, I want to talk about recursion. So recursion is an amazing concept. It will be used in a lot of data structures that we'll be studying throughout this course. And it happens to be my favorite topic, and I hope it will be your favorite topic as well. Once you go through the next couple of lectures, including this one, I think you'll get very like a lot of clarity on what recursion is, how to use recursion, and how it can make your life very easy. Okay, so if you ask anyone what is recursion, most of the times people will say that recursion is when a function is calling itself. Now, why will a function call itself? I have asked a function to do some work for me and now it's calling itself. That doesn't really make a lot of sense. So why will that happen? Okay, so a function can call itself when the function is saying, okay, you want me to calculate, for example, let's say n factorial. I hope you know what n factorial is. N factorial is n into n minus 1 into n minus 2 up to 1. Right? Multiplication of first n natural numbers is called n factorial. So I want a function to calculate n factorial for me. Now the function is saying, I can do that, but my life will be so much easier if you give me the answer to n minus 1 factorial. If you give me the answer to n minus 1 factorial, I just have to multiply with n. This is the function talking. So the factorial function is saying, calculating n factorial is super easy for me if I know the answer to n minus 1 factorial. I'll just multiply the answer with n and I will be able to give you the answer which is required. Okay. So, and obviously we can calculate n factorial using a for loop, a basic for loop, and keep multiplying numbers for I in range 1 to n plus 1, and we'll be able to do that, right? So I'm taking an example of factorial because the first few examples that I'll be taking, they will all be very simple examples that you can use, that you can resolve, like that you can calculate, you can solve those problems using iteration and without using recursion. Iterative solution is when we are using for loops or basically just iterating through whatever code that you might have written without using recursion so far. Okay. So the first few examples will be because we want to learn recursion, but later examples will be which become so much easier if you're using recursion, which become really hard when you are trying to solve them using iterative methods. Okay. So in case of factorial will say, hey, you want me to calculate factorial n? I will do that, but to do that I will call myself with a smaller input, and then once I have that answer, I'll multiply that with n and I'll have your answer as well. So recursion is when a function is calling itself with a smaller input, which basically is easier to calculate, right? So finding factorial n is a little harder than finding factorial n minus 1. Now factorial n minus 1 internally will call effectively factorial n minus 2 and so on. So this ways we are reducing the size of the problem one by one till it becomes absolutely easy. It becomes absolutely trivial. And when that trivial case is like when we reach that trivial case, we will basically just return the output and we will not call recursion after that. So for example, if I say find 5 factorial for me and then you say, oh, I can find 5 factorial if you find 4 factorial for me, then I say for that I need 3 factorial, then I say for that I need 2 factorial, then I say for that I need 1 factorial, for that I need 0 factorial, then I'll say I need minus 1 factorial, minus 2 factorial. There is no stopping that. So we can't keep going like this. We have to stop somewhere and say, oh, this is very easy. This I already know, so let me just return the output corresponding to 0 factorial. So that if I start from 5, 5 says give me 4, 4 says give me 3, 3 says give me 2, 2 says give me 1, 1 says give me 0, 0 will say, okay, here is your answer. Using that, 1 will calculate its answer and pass it to 2, 2 will calculate its answer and pass it to 3, 3 will calculate its answer and pass it to 4, and 4 will calculate its answer and pass it to 5, which will basically give us the output that we wanted this function to calculate for us. Okay, so that's how recursion is going to work. Perfect. So let's quickly write this factorial code. Okay, so let me quickly create a notebook. Okay, so I have n which I'll take user input. Great. Now I need to write a function. So we will, in recursion, we'll always using function. You cannot use recursion without actually writing functions. So let's write a function factorial which will get an input. Okay, let me move this just to avoid confusion. Sorry. Wow. Just 1 second. Perfect. So I'll call the function in this cell, but let me write the function here. So what are we saying? I want to say that I want to return n into factorial of n minus 1. But there is a problem with what we have written so far. We haven't given the trivial case. We call that case base case. So we haven't given the base case. So having a base case is very, very important, because otherwise, okay, so let's take an example. I take n is equal to 2 and I call factorial 2. Factorial 2 will say, hey, give me factorial 1. Factorial 1 will say, hey, give me factorial 0. Factorial 0 will say, hey, give me factorial minus 1. That'll say, give me minus 2. That'll give me factorial minus 3, factorial minus 4, and so on. It will never stop. So you'll never get your output. So we need to give that trivial case. We'll give that, but for now, let's just call it without the trivial case and let's see what happens. Okay. So it's asked, sorry, I should not say factorial 2. I want to do factorial n. Let me stop this. Run this again. And it's running, right? It's continuously running. The star here shows that it was running. There was a star here which showed that it was running. It was not done yet. And now it's giving us an error, maximum recursion depth exceeded. This basically means I called 2, went to 1, went to 0, went to minus 1, went to minus 2, and it kept going, kept going, kept going. And there is a limit to how deep you can go in recursion. Till how long you can keep going, there is a limit to that. There is a limit because there is memory use, right? So when 2 is waiting for 1, there is a function which is waiting. And because it is waiting, there is some memory which is used by this. So if you have an infinite number of functions being called, you will require infinite amount of memory, and you can't have infinite amount of memory. So you need to have some restriction of how long or how deep your recursion calls can be. Okay, so by default Python has nearly 1000 depth, right? By default, right? So you can change this and we'll see how to change that, but by default you can go deep up to 1000. At least in my system I can go deep up to 1000. Okay, perfect. So seems like we need to add the base case. If we don't add the base case, the code is not going to work. So base case is very, very simple. Before I make the call, which is factorial minus 1, I just need to say if n is 0, return 1. Right? That's the base case. If it is 0, then I don't have to do anything. 0 factorial is 1. That is by definition. So let's run this again. Let's give it 2, and we get the output very quickly, which is 2. 2 factorial is 2, 5 factorial is 120, and that's exactly what we are getting as well. Okay, so I hope this is clear, right? You could have, there was no difference. I could have written this function, the same function, in a little different way. Let me call it factorial 1 for now. I could have said small output is equals to, there is no difference in the above function and this function. right? I could have said this, but that doesn't really matter. So what am I saying? I'm saying I want to call factorial n minus 1, whatever is the answer, I'm going to use that answer to multiply with n. And that's the same thing here as well. Doesn't matter, right? So both of these functions are exactly the same. So now you know how to write factorial. In the next session, we will actually talk about what exactly is the math behind recursion and why does it actually work. Okay, thank you. Hi. So in this session, I want to talk about the math behind recursion and why exactly does recursion work. So recursion is actually based upon a very neat mathematical concept called PMI, Principle of Mathematical Induction. So PMI was a concept that we could use to prove a lot of things, right? For example, if I want to use PMI to prove that sum of first n natural numbers is equal to this formula. So I can use PMI to prove this. What exactly is PMI? And we'll see in parallel how to prove this particular statement. So PMI basically says, if I want to prove a fact, let me not call it fact because it will be confusing with factorial. Let's say I want to prove a statement f. Okay, I want to prove that f is true for all natural numbers. Let's say I want to prove that. So PMI says, first of all, prove that it is true for f of 0 or f of 1, take a very small number and prove that this is true. That's your first work, task 1. You are supposed to prove that f of 0 and f of 1, or maybe 1, maybe both, is true, right? That's the first thing we need to do. Then PMI says, assume f of k is true. I can assume f of k is true. Task 2, prove f of k plus 1 is true. That's what we need to prove. So the middle one is not your task. Your task is proving a very small case and assuming that the middle one is true, that is f of k is true. Using this statement, you need to prove that f of k plus 1 is true as well. Okay? This is not something that you have to prove. This is an assumption. Do not question this. You need to prove this. Okay? Let's apply on this particular statement. So first of all, let's work on our task 1. That is sigma 1 is equals to sum of first natural number. That is 1, right? And so my LHS is 1. My right hand side is 1 into 1 plus 1 by 2. N is 1, right? So this is equal to 1 into 2 by 2, which means 1. So my LHS is 1, my RHS is 1, hence proved. So my base case, my task 1 is proved. Okay. So now I can assume sigma k is equals to k into k plus 1 by 2. So I can assume this. Now using this assumption, I need to prove task 2 that I have is sigma k plus 1 is equal to k plus 1 plus 1 by 2. This is something that I need to prove, right? So this is my task. This is what I need to do. Okay, so let me clear this out. So I can assume this is true and I need to prove this. Okay, so let me take the LHS. Sigma k plus 1 is equals to sigma k plus k plus 1, right? Sum of first k plus 1 natural numbers is sum of first k natural numbers plus k plus 1. Okay. Now we already know what is sigma k. Sigma k is k plus 1 by 2 plus k plus 1. Okay. So I'm going to multiply this with 2 and divide by 2. Now from both these you can take k plus 1 by 2 common. So this is k plus 1 by 2, this is k plus 1 by 2, so remaining is k plus 2. And that's exactly what you needed on your RHS. So LHS has become equal to RHS. So that basically means I have proved that sigma 1 is equals to 1 into 2 by 2. This is done. This I assumed. I don't have to prove this. And using this, I have proved this. PMI says now you have proved that sigma n is equals to n into n plus 1 by 2. You don't have to worry about this statement anymore. This is definitely true. Okay. So the middle statement is an assumption. The last one is a proof. But this is a little weird, right? I just proved for a small number. Then I made this huge assumption. Now using this assumption, I proved just one tiny step. And you are saying that it's going to work for all natural numbers. So it sounds a little weird. But actually it's not that weird. The way it is working is, I have taken a generic k, right? I took k and I proved it for k plus 1. I know where to start from. I know the base, right? I know it works for 1. Now using 1, I can prove it works for 2. So if I take k's value to be 1, then I prove that it works for 2. Now using 2, you can prove it for 3. So the way it works is, I have told you, you know how to stand. So you are able to stand here. And I have taught you how to take a single step. Now you can keep taking steps and you can keep going higher, right? You know you can start from somewhere and then you know you can take a small step. You know that. So by taking these small steps, we can prove it for all natural numbers. So 1 allows us to prove it for 2, 2 allows us to prove it for 3, 3 allows us to prove it for 4, and so on. It will work for all natural numbers. Recursion is exactly like that. Whenever we will be talking about recursion, we will look at the base case as the first step of our PMI. We call it the base step, the base case. The assumption PMI says is induction hypothesis. Okay, that's the induction hypothesis. That's the assumption that you can take. And the last step is the induction step, when you need to prove using the hypothesis that you are actually going in the right direction. Using a smaller, using k, you need to prove it for k plus 1. Now if you look at factorial, that's exactly how we wrote our code as well. We proved, we wrote the code which works for factorial 0. We are absolutely sure our code works for factorial 0. Now if I assume that my code works for a factorial of n minus 1, I have written code which will definitely work for factorial n. So I have taken care of this. My code is assuming this will work. And if this works, this will definitely work, because if this is giving me the right answer, I'm just multiplying with n to get the n factorial value as well. Okay. So this is basically what we'll be applying in all our recursion problems. That's how you should think about recursion. Hey, what is my base case? What is my hypothesis? And what is the induction step that I need to take care of? Okay, that's exactly how we will be using recursion throughout whatever problems that we'll be solving. Perfect. Now let's pick up few more problems in the next few sessions, and hopefully that will give you a lot more clarity on whatever we have talked about so far. Thank you. Hi. So now let's code few problems to basically get a little more understanding of recursion, right? So the first problem is very similar to factorial. It's actually almost the same. So I just want to find sum of first n natural numbers, and I don't want to use the formula. I just want to actually find the sum starting from 1 to n. Okay, so if you look at the base case, we can take the base case either to be 0 or to be 1. So let's take the base case to be 0. So if n is equal 0, the sum is going to be 0. And to find sum of first n natural numbers, let me just change the color. So if I want to find this, I can say this is equal to this. So I'll find this output, and once I have this output, I can just add sum and return. Thinking from PMI perspective, I'm taking care of base case. I'm assuming this smaller problem will give me the right output. If I get the right output from this smaller call, then I am making sure that I am doing the right thing, because if this is correct, this is definitely correct. Okay, so that's what I want to do. So let's quickly do this. I'm going to add a function here. Okay, sum till n. So if n is equal 0, I'm going to return 0. Otherwise, my small output will be sum till n minus 1. So I get the sum till n minus 1. So the trick here is, do not worry about this particular line. This is our induction hypothesis. We don't have to worry about this. This is an assumption that we need to take. Most of the people get stuck with recursion because they will go inside this to think about how exactly n minus 1 is working. N minus 1 is not going to work till you complete this function properly. We haven't completed this work yet. So the idea is that this is our induction hypothesis. I'm assuming that this is going to work fine. I've taken care of base case, induction hypothesis I'm assuming, and now my output will be equal to the small output plus n. If small output is correct, I'm making sure that my output will be correct as well. That's the induction step that I need to take care of. And then I can return the output. Okay, so let's find factorial, and let's also find this. Okay, let me run all of this again. I don't think this is a new notebook, so this isn't actually, so we haven't compiled this function, we haven't run this function, not compiled, we haven't run this function in this notebook. This is a new notebook, which is a copy of the previous one. So let me just redo this, and now let's run this. So 5, okay, let me just print out these. It's only printing the output of the last one. Right, so let me print out these. And 5 factorial is 120, and sum of natural numbers till 5 is actually 15, which is correct. Okay, so seems like our code is working absolutely fine here. In the next session, we'll pick up another problem, but in the meanwhile, please practice 1 or 2 problems which are given to you within the lecture. Okay, thank you. Hi. So in this session, I want to talk about another problem, and we'll solve it in 2 different ways. Okay, so I want you to print numbers from 1 to n. Okay, so I want you to print numbers from 1 to n. So you get your function will get an input as n, and then you need to print numbers from 1 to n. I want to print it this way. I also want to print it this way. Okay, so I want to print it both the ways. Okay, so the base case. Now the base case can be either we can take the base case to be 0, in which case we don't do anything. If you ask me to print from 1 to 0, I won't do anything, right? If you ask me to print from 1 to 1, that can be another base case, in which case I'll only print 1. So now we can decide whether we want 0 to be a valid input to our function or not. If you take 0 to be a valid input, in that case, basically what you are saying is that I'll get a 0 and I won't print anything, because I'm supposed to print numbers from 1 to n. So if you ask me to print from 1 to 0, I'm not going to print anything. Okay, So let's quickly write another function, print 1 to n. So in this case I'm going to print from 1 to n, and I'm going to get an n, and I'm going to take 0 to be a valid input. So if n is 0, I'm going to return nothing. I don't have to return anything, I just have to print. So I'm returning, that basically means I'm not going to do anything. Otherwise, what do you need to do? Okay, so you want to print numbers from 1 to n. I've taken care of base case. I can assume that the function will work for n minus 1. That means if I call this function with n minus 1, it will print these numbers. So it will print till n minus 1. And if it prints till n minus 1, what do I need to do next? I just need to print n. Okay, so using induction hypothesis, I am going to print from print 1 to n. I'm going to pass n minus 1, and once I have printed numbers from 1 to n minus 1, I am going to print n. So 1 to n minus 1 is taken care by recursion. I am printing n and I am done. So I can just empty return, or I can just not write return at all. Okay, so let me run all the cells and let's give an input. Okay, I didn't call this function, so let me call the function as well. Print 1 to n, and I'll pass n. Okay, so I'm able to print numbers from 1 to 10. Okay, so we didn't do this in case of factorial and sum of numbers till n. Let's try to see what exactly is happening in this call. Okay, let's see what exactly is going on here. So I gave it 10 as the input. So what happened? 10 is not 0. So you went to a function print 1 to n. Let me call it p as a short form. You called p10. So for this function, n is equal to 10. So it said, is n 0? No, n is not 0, it is 10. So I asked it to call another function p of 9. Within this p of 9 function, your n's value is 9. Because you passed n minus 1, so when you come to this function again, this time the argument that you're getting, the input that you're getting is 9. Is 9 0? No, it's not 0. So I'm going to call again at 8. See, while you're writing the code, don't try to see what is going on, what exactly is recursion doing. Honestly, please don't do that. You need to believe PMI, you need to treat recursion problems like theorems. You need to prove, you need to make sure that you apply each step of PMI properly and your function will work. But once you have written the code, it's not a bad idea to actually see what exactly is going on. So we haven't printed anything yet. P8 is calling P7, and for this n is equal to 8. For this n is equals to 7. Now it's going to call P6, so on up to P of 0. P of 0 will not print anything and it will return. So now P of 1, when you came here with n is equals to 1, it had called P of 0. That has returned. So P of 1 can continue its work. It's going to print 1. So the first thing that's going to get printed is going to be 1. Why? This was the first function which got called, but it didn't print anything. It called P9. Now P10 will print something only when P9 has returned. So P9 doesn't print anything till P8 returns, and so on. So no one has printed anything once you reach P0. After P0, when P0 is returning from here, from the base case, P1 is going to print using this statement, 1 is printed. Then P2, who was waiting for P1, is going to print 2, P3 is going to print 3, P4 is going to print 4, P4 is going to print 4, and so on. Eventually P10 is going to print 10, and that's how we are getting our output. That was exactly how this was working as well. It was exactly working the same way. You asked it to find sum till 5. It said, okay, I'll do that, but let's first call sum of 4. Because 5 was not 0, it called sum of 4. Sum of 4 said, okay, I'll do it, but let me first call 3. Then it said, oh, okay, let me call 2. Then it said, oh, let me call 1. Then it said, okay, let me call 0 first of all. And 0 said, oh, I'm not going to call anybody else. I know what the answer is. It's 0. So it returned 0. When it returned 0, sum of 1 said, okay, so my small output is 0. So my output will be 0 plus 1. Because for sum of 1, n is equals to 1. So it's returning 1. With the same logic, sum of 2 is going to return 3. Because for sum of 2, the small output is 1. It's adding 1 plus 2, 3. Now if you look at sum of 3, it had called sum of 2. So in case of sum of 3, the small output is 3. So it's going to return 6, it's going to return 10, and this is going to return 15. One thing that you need to understand, small output, n, all these variables are created for each of these functions. And they are their local copies. Just because sum once small output is 0 does not mean it has put the value of 0 in all the small outputs. Each function has their own copy of small output and they are storing their own value. Okay, so that's how recursion is working. It's doing a lot of work, but if you use PMI, you don't have to worry about all this work and you can just focus on the 3 basic steps: base case, induction hypothesis, and the induction step. Okay, perfect. So we have printed from 1 to n. Now I want to print n to 1. The reverse printing. Okay, it's actually going to be very, very similar. I want to print n to 1. So n has to be, so again the base case, if n is 0, I'm going to return, I'm not going to do anything. Now, you have to print from n to 1, right? That means n should be printed first and then the last one should print to 1. So if I call the function to print, let's assume that induction hypothesis works. So what you will do with that assumption is print n to 1, we'll call n minus 1. So I'm going to assume that by making this call, I have printed n minus 1, n minus 2 up to 1. And once I return from this function, if I do exactly what I was doing in the earlier function, and once I return and I print n, then what is going to happen? I don't think we have implemented the induction step properly. The base case is correct. Hypothesis is fine. You are saying this call will print n minus 1, n minus 2, n minus 3 up to 1. But what have you done? You have printed n after this, after the call. You haven't done the induction step properly. So this function is not going to work the way you intended it to work. N should have been printed before doing all of this. That basically means everything else is almost correct. Everything else is almost fine except this. This was the only mistake that we had. Now once I've done this, let's see if this is going to work. Base case is correct. My induction hypothesis is it's going to print from n minus 1 till 1. And before it prints any of this, I am printing n myself. So I have done my work correctly, and now if this function works properly, the whole thing works properly. And I can assume this function works properly because that's my induction hypothesis and it's going to work fine. Let's run this and see if it actually works fine. This time let's try n to 1. 5. Okay, so I want to run this cell. That's the problem. Okay, and you get 5, 4, 3, 2, 1, and it's working fine. So how did it work? P n to I, you got 5. It said, okay, 5 is not 0. It didn't say I want to call 4. It first said, hey, I want to print 5. So it printed 5 first. Then it made a call to 4. 4 said, hey, I'm not done. I'm going to call 3, but before I do that, let me print 4. So it printed 4. Then it made a call to 3, which basically first printed 3, then it made a call to 2, which printed 2, then it made a call to 1, which printed 1, then it made a call to 0, and 0 said, I don't want to do anything, let's return. It returned here. You returned to 1. 1 said, I don't have anything else to do. This was the last thing that I wanted to do. So 1 returns to 2, 2 returns to 3, 3 returns to 4, 4 returns to 5, and 5 returns to the caller of the original function. And you have printed the numbers in reverse order. What I wanted to tell you in this, it's not necessary that you have to make the recursion call first and then do your work. It's possible I'll do my work first and then I'll make my recursion call. But PMI still holds. It works absolutely beautifully if you think it the right way. Okay, perfect. Again, please write couple of codes. Please write all the code that is coming in between the lecture, in between the sessions. Only then you will be able to take the maximum benefit out of the next session. So in this session, I want to pick up a new problem called Fibonacci series. So the problem is that I'm given an n and I need to find nth Fibonacci number. So what is Fibonacci series? Fibonacci series starts with 2 1s. Some people say it starts from 0, but I'm going to pick it from 2 1s, right? So the first 2 numbers are given, 1 1. The next number is sum of the previous 2. The next number is sum of previous 2. The next number is sum of previous 2. The next number is sum of previous 2, and so on. So this is your Fibonacci series. So in a way I can say Fibonacci of n is equals to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Now the optimal way of finding nth Fibonacci number will be to do it iteratively. You take the first number, second number, you find the next number, update first and second, and then basically keep finding the next number. Right? Store the 2 just before the next one and then keep finding the next number and keep updating these numbers. But here we want to use recursion to do it. It will be not the best solution. The best solution will be iterative, but it will help us understand recursion better. So if somebody asks me to write code for Fibonacci, I'm not going to use this code. But if somebody asks me to use like find Fibonacci number, like the nth Fibonacci number using recursion, then I'll be doing this. But this is a very good example to learn recursion. Okay, so this is the formula that we can use, right? This is the equation that we can use. We will need a base case. The base case is that Fibonacci of like the first number is 1, right? The first number is 1. Okay, so let's write code for this. Okay, so fib of n. This is not going to work, whatever I'm writing, so don't worry about that, but we will correct it in some time. So if n is equal to 1, I'm going to return 1, because that's my base case. If you are going to ask me for the first Fibonacci number, I'm going to say 1. Okay, now I need to find fib of n minus 1. That I can find using my own function by calling fib of n minus 1. And you want me to find fib of n minus 2. And you can actually use your own function to calculate that as well. Because while in an extended form of PMI, you can actually assume, once you have proved the base case, you can assume the hypothesis can be that I'm going to assume 1 to k everything is true, and I'm going to use this to prove k plus 1. Let me repeat that. So in case of PMI, we have discussed that I need to prove the base case. Once I prove the base case, I was saying I can assume that f of k is true. Using that, I was proving f of k plus 1 is true. Extended form of PMI says, assume f of 1 is true, assume f of 2 is true, assume f of 3 is true, assume f of k is true. Now using all of these, can you prove f of k plus 1 is true or not, is going to define whether you can prove f for all natural numbers or not. Okay, so not just for k, you can assume for everything. That means I have to do it for n, so I can assume it's going to work for n minus 1, I can assume it's going to work for n minus 2. Okay, so before we go to the code again, let's first talk about this extended form a little. Okay, perfect. So we were saying earlier that using 1 I can prove 2, then using 2 I can prove 3, then using 3 I can prove 4, right? Now using 1 you can prove 2. Now to prove 3, what is the harm if we use both of these? Because we have already proved 1 and 2. Can I use 1 and 2 to prove 3? I should be able to do that, right? Because I have already proved 1 and 2. Now when I proved 1, 2, 3, all 3, can I use these to prove 4? I think I can. Why can't we use all of them when we have already proved them? Why do we have to depend upon just the previous one? So this is basically the intuition behind the extended form of PMI. Okay, so I can assume for n minus 1, I can assume for n minus 2 that my function is going to give me the right answer. Once I have n minus 1 and n minus 2, my output will basically be fib of n minus 1 plus fib of n minus 2. I just named my variables in this way so that it becomes easier to recall what we are trying to do. And then I can return the output. So this function is almost correct. There is a small issue with this function that we will see. Okay, let's try to call this. N is equals to 4. Let's find the fourth Fibonacci number and let's call fib of n. And it seems like it keeps running. But I can say that by looking at the star. And now it has returned and it's saying maximum recursion depth exceeded. That means we kept going in recursion and we never came back. Like it crossed the limit that you are allowed to use. Okay, that's weird because it's a very small input. We shouldn't see this error for such small input. Now what exactly is happening? So you got 4 as your input. For 4 you said, hey, I need 3 and you said I need 2. For 3 you said I need 2. Now it's going to work on 3. Once you return the answer for 3, then it's going to call for 2, right? So first it has to complete this line. Once you're done with this line, then it's going to make the next call. So for now 4 has called 3, 3 has called 2 and it's going to call 1 when it comes back, when 2 comes back. 2 is calling 1 and 0. Okay. For 1 you know the answer, that is your base case. But 0 is not your base case. So 0 is going to call minus 1 and minus 2. Wow. And as soon as it goes to minus 1 and minus 2, there is no stopping after that. It will keep going down. Recursion will keep growing. So seems like if you call Fibonacci of 2, the first call you make is Fibonacci 1. That works fine because Fibonacci 1 is a base case, it's going to return 1. But then 2 goes ahead and calls Fibonacci of 0 as well. And as soon as you call Fibonacci of 0, things go really bad. Okay? Okay, so what is the solution? In some cases you need to look at, do you require one base case or multiple base cases? In this case we need at least 2 base cases. And I think that's very obvious by looking at the Fibonacci series. If I give you only one Fibonacci number and I tell you find the rest of Fibonacci numbers, I don't think it will be possible because what you need is, hey, this one has to be sum of this and the one before it. I don't know what is before this. So I think to start the Fibonacci series, I need at least 2 numbers. That's required. At least 2 numbers are required. And by looking at recursion and how exactly recursion calls are working, it seems like we will need 2 base cases and not just 1. Okay. So 2 is going to call 1 and it's going to call 0. So either I need to pass the 0th Fibonacci number or I should have the second Fibonacci number, so that when 3 calls 2, it returns directly, when it calls 1, it returns directly, and we don't fall into this infinite recursion problem. Okay, so in this problem we will not require just one base case, we will actually require two of them. Sorry, or if n is 1 or n is 2, so there is no 0th Fibonacci number the way I am writing code. There is only first Fibonacci number, which is 1. There is second Fibonacci number, which is also 1. Now this should work better and we should get the right output, which is the right output. So first Fibonacci number, second Fibonacci number, third Fibonacci number, and the fourth Fibonacci number is 3. So we get the correct answer here. Now let's see how exactly it is working. And again, I want you to notice I've written all the code, and now I am asking you to let's see what exactly is recursion doing, what exactly, like how deep it is going, and all of this, how exactly it is working. Okay, so let's say we call for fib of 5. Fib of 5 is going to say, hey, I need 4. That's the first call it's going to make. That's the first call it's going to make. 4 is going to say, hey, I need 3. 3 is going to say, hey, I need 2. 2 is going to say, hey, I need 1. Sorry, 2 won't say anything because 2 is the base case. So 2 will return 1. Now 3 has got the answer for the first call. So 3 is going to make the second call, which is 1, which is also a base case, so it's going to return as well. So 3 gets 1 as fib n minus 1 and 1 as fib n minus 2. So 3 is going to return the output as 2, which is sum of both these sides. Now 4 has the output from one side, from n minus 1. 4 is going to make another call to 4 minus 2, which is 2, and 2 is going to return 1. And now 4 is going to return 3, and 5 is going to say, hey, one side gave me answer, which is fine, I need another answer, which is 3. So this is in case we had called on 5. We have called on 4, but if it was on 5, this is how things will work. So 5 is saying, hey, I have the answer from 4, that means this is done. Now I need to call this. So it's going to call on 3. What is 3 going to do? 3 is going to say, I am not 1 or 2, so let me call on 2. That's the first line here. And 2 is going to return 1. 3 is going to call on 1, which is going to return 1. And 3 is going to return 2, because this is the sum of 2 calls that 3 got. Then 5 will return 5, which is the correct answer for 5th Fibonacci number. So it's doing a lot of work, right? We don't see it, but it's doing a lot of work for us, and it's finding the answer for us. So I particularly like the fact that recursion problems are recursion solutions are very concise, right? Okay, find me n minus 1 Fibonacci number, find me the n minus 2nd Fibonacci number, and then I'll give you the output, and I'm done. I'm not doing much here. I'm just like, it's like I'm asking for things more than what I am actually doing. But everything is done by me as well. Like all the code I've written here, we have written that code. So nobody else has written this code. But this is a very smart code which basically does all the work for us without we having to think of the nitty-gritties. Okay, perfect. So in the next session, we'll start looking at a little more interesting problems around arrays and how to use recursion along with arrays, or I can say lists. Okay, thank you. Hi. So in this session, I want to talk a little about the recursion depth error that we kept getting, right? So the cases that we saw, we were actually falling into infinite recursion. So any language will basically fail for cases like these. But now let's see, can we have that error while our code is actually correct, right? So for example, this is the code that we wrote in case of when we were learning factorial, right? So this is my factorial function. I'm calling this, I'm giving 5, it works absolutely fine, works great. Let me give 100, works perfectly fine, hopefully. Like, I can't confirm it is 100 factorial, but we have written the right correct code, so it should be working fine. Okay, 500 works absolutely great and also works quickly. 800 working fine, huge output, but you have done multiplication, right? Like, so it's pretty huge. 800 factorial is huge. So now let's give 900, still works fine. Let's give 1000 and you're getting the right answer. So let's run it again. Let's give 2000 this time, and it's not returning. It should have returned by now, and now we get an error which says maximum recursion depth exceeded in comparison. So that means we have hit the limit of the amount of recursion calls that you can have in Python, right? So let me try, let's see what that limit is. Let's try this. So it works for 1001. So it seems like this system does not have the 1000 limit that I talked about in an earlier session. So it must be something else. 1400 also works fine. 1900 also works fine. 1998 doesn't work. So this is going to give us an error. Okay. 1950 also works. So it's nearly 2000 on this system. Now a lot of problems would require you to have much, like for example, if I want to find factorial of 10,000, there is no way I can do it using recursion if this is going to be the limit that we are going to work with. So in case you want to update this limit, there is a way of doing it. It's not recommended because it takes a lot of space, so you have to be sure that it's not going to eat up too much space. But if you want to change it, we can change it. So there is a library called sys. You will need to use that to change this limit. Okay, so I'm going to import sys, sys, and within sys you can set the recursion limit by calling this, and you can pass the recursion limit that you want to set. So for example, I'm setting 3000. I'm going to call it 2000 and it works fine. So seems like the recursion limit has been increased. So you have to be a little careful when you want to do this, when you don't want to do this. But whenever you do this, if in case you hit a problem where you have to increase the size, otherwise your test cases are not passing or whatever is happening, in that case you would need to increase the recursion limit. Okay, so please make sure that you understand this. Please try it out, try running factorial for large numbers and see what exactly is the depth limit in case of your system, and then you can change it if you need to. Okay, so that's the only thing that I wanted to discuss which is specific to Python. Generally the depth is not so less in case of Java, CPP or other languages, but in case of Python the limit is around 1000 or maybe 2000 in this particular system. So you can update that if you want to, but you have to be careful. Okay, thank you. Hi. So in the next couple of sessions we'll be solving a problem which is actually pretty easy when you're doing it iteratively. It's easy with recursion as well, but we are doing it using recursion because it will teach us a lot about recursion, and that will allow us to solve very interesting problems later on. Okay, so the problem that we want to solve is given a list, we want to check if it is sorted. So we are given a list and we just need to check if the list is sorted or not. Okay, so we have a list which has some elements and we want to check if it is sorted. Now obviously it's very easy if you are allowed to use a for loop. What I am saying is no, let's do it using recursion. Okay, perfect. So how do we do it using recursion? So very simple way to look at this is, let's say the base case, right? So let's first talk about the base case. If my list is of size 0 or 1, then it's by default sorted, right? If you just have one element, is the list sorted? Yes, it is sorted. If you don't have any elements, even then the list is sorted. So by default, that's our base case, right? Induction hypothesis. I'm going to assume that for list of size L minus 1, my function works. whatever function I have written, I have not written anything, but whatever I'm going to write, I'm going to assume it works for L minus 1. Induction step. The fact that my function works, that basically means it will tell me if this much list is sorted or not. Now my function can tell me two things. Either it can tell me yes, it is sorted, or it can tell me no, it is not sorted. In case it's not sorted, in case this part is not sorted, then definitely the whole list is not sorted. So I can just return false. So if I get a false, I'm going to return false. I don't have to do anything else. In case my function returns that this part of my list is actually sorted, then there is only one part which is left. I just need to make sure that this element is smaller than this element. For example, let's say this was the list given to me, 11, 2, 3, 4, 5. Now this part, is it sorted? Yes, it is sorted. But is the whole list sorted? It's not sorted because the first element is not smaller than the second element, smaller or equal than the second element. So it's not sorted. Okay, so that's how we are going to do this. We have two options. The way we have seen it earlier, we have two options here. One option is I'll check upfront. Before I make a call to this part, I'm going to check if this is greater than this, I can return false. I don't have to make the recursion call in case 11 is actually greater than 2. Because the first number is larger than second. Now irrespective of what is in the rest of the list, this array or this list is not going to be sorted. Okay, so I'm going to first check if this order is fine, then I'm going to call on this part of the list and this will return me the right thing. This function will work fine because I am taking care of base case, I am taking our induction step, the induction hypothesis is going to work fine. Okay, let me quickly repeat our base case. Length is 0 or length is 1, return true. Induction hypothesis, it works for L minus 1 sized lists. Induction step, I'm going to check if the first element is greater than the second element, I'm going to return false because that's not allowed. In case this is not true, else, that means the first two elements are in the right order. In that case, I just need to check for smaller list starting from 1 till the end. I'm going to call my function on this smaller list, and based upon that output I'm going to return my output. Okay, so let's write this code. Perfect, is sorted. I'm going to get a list. Call it, I don't want to call it L, let me call it A. Right, let's store the length of A in L. So I have the length of A. Base case says if L is 0 or L is 1, then I can return true. Then I can return true. So that's taken care of. The base case is taken care of. Now we have an option. You want to call on the smaller list first and then check for 0 and first element, or you want to check for 0 and first element first and then call recursion. Either ways, right? So what I mean here is I have this list. Do I want to do this comparison first and then call on this list, the smaller list, or do I want to do all this work first and then do this comparison? I think it's better to do the comparison first. In case the first element itself is larger than the second element, why to call recursion, why to go through rest of the list, right? So I'm going to do this. In case my list's 0th element is greater than first element, then I can return false. Now if you have reached this point, That basically means your list is of at least length 2. It's not of length 0 and 1. It's of length 2 at least. And the first 2 elements are correctly ordered. Now we need to call on the rest of the list. So this array A, this list A is this. I want to call on a part of this list. Just one part of this list, not the whole list. And if this part is sorted, then the bigger list is also sorted because the first 2 are correctly placed. And in case this is false, then I'm going to return false. Okay. How do I get this smaller? Okay. Let me call this is smaller list sorted is equal to, I'm going to call is sorted. And I need to pass this smaller list, the list starting from here till here. I need to pass this. Now that's the tricky part. You basically will have to create a new list B, which will be this, right? Which basically means you're copying everything in A into a new list B. Whatever you have in A, except the first element, you're copying everything. You're making another copy and you're keeping it in B. It's heavy work. If I have a list of 1000 elements, that means I'm copying 999 of them into a new list. For now, let's do this. Right? For now, let's just do this. Smaller list is equal to A. I'm doing slicing, right? So is smaller list sorted? I'm calling is sorted on the smaller list. And now if the smaller list is sorted, then I can return true. If it's not sorted, then I can return false. Again, not needed. This much code is not needed, but it's okay. Right? Let's not worry about that. I could have written it in a single line. I could have just return is smaller list sorted. Because in case it is true, you are returning true. In case it is false, you are returning false. That means you are just returning this. Here you are just returning is smaller list sorted. Because if it is sorted, then you are also, your bigger list is also sorted. If it is not sorted, then bigger list is also not sorted. So either ways, this is also fine. So this code should work, but this is a line which I don't like much, because just think about it. I'm given a list of 1000 size. I'm making a copy of 999 size. I'm calling function on this again. That function is going to make a copy with 998 elements copied and call recursion on this again. Then a copy with 997 elements, then a copy with 996 elements. Huge requirement for space. You're saving way too much data. Okay. Okay. Let's create a list. Is sorted, and it says yes, it is sorted. Let's put something else in between. It's saying no, it's not sorted. Seems like our function is working fine. I've told you what's wrong with this function. What's wrong is it is making too many copies of the data that we have provided it. In the next session, we will improve that. We will not make copy of A, instead we'll figure out a way of using the same list in all the functions. Okay, thank you. Hi. So in this session, we just want to do a small change in the previous function that we had written. We have this list and we were making a copy of it, copying all the data from here to here to do a recursion call. In this session, I just want to do a small change. I don't want to make copies. So instead what I'm going to do is, I'm going to tell my function, hey, you need to start working from here. Don't look at the list before this particular index. So initially we will have to work on the complete list, so the start index will be 0. So I'll compare 0 and first element. When I make the next call, I'm not going to make a copy of the list. So I'm going to say, hey, don't worry about the 0th element, you need to start looking at from 1. In the next call, I'm going to say, hey, don't worry about 0 and 1, you need to start looking from index 2, and so on. That's how I want to change my function. So now my function is going to get a list, and it's also going to get a start index. In case your start index is equals to length minus 1, what does this mean? This basically means start index is here. I just have one element left. And in case you have one element left, it's sorted, right? You don't have to worry about it. So I'm going to do two things here. Just to handle the empty list case, I'm going to check if length is 0, or I can say if SI is equal to L or L minus 1. This is going to be a case only if you give me an empty list to start with. Okay, so if this or this is the case, then this is my base case. I'm going to return true. And if that's not the case, that basically means I have a list, you have given me a starting index, and I need to check from here to here if the list is sorted or not. I'm not going to worry about this part. We'll apply exactly the same logic using on this smaller part. So what was our logic? We'll compare the element at SI and the element at SI plus 1. That is the first two elements of the part that we need to work on. If they are in wrong order, we'll return false. If they are not in wrong order, we need to make a call on this part, one smaller part, which I can do by passing SI plus 1 to the next recursion call. Okay, which we can do by calling SI plus 1 on the next recursion call. Great. So let's create a new function. Is sorted. I'm going to, for lack of creativity, I'm going to call it is sorted better. A comma start index. And what did it say? Let's first calculate the length. If SI equal L minus 1, that means there is only one element left in the list. And just to handle the 0 length case, I'm going to say this, right? Sorry. So what am I saying here? If SI is equals to L means that you have completed the list. SI is equals to L minus 1 means you have only one element left. So I'm handling both the cases. In this case, I'm going to return true. Otherwise, let me just clear this output. I don't like this error. Okay, so I'm going to return true. Otherwise, we are going to compare. So previously we were comparing 0th and the first element. Now I'm not going to worry about the 0th and the first element. I need to worry about the starting index element and the starting index plus 1 element. Anything before the starting index is not my problem. So if this is the case, I'm going to return false. And now, if that is not the case, if you have reached below this if, that basically means the first two elements are in order. So I need to check is smaller part sorted. So I'm going to call is sorted better with the same array, and this time I'm going to pass SI plus 1, start index plus 1. So what's happening here? This is for my list. You asked me to check it from here. I've checked the first two elements. Now I am calling the same list by passing the next index. This way the list will keep getting smaller, and eventually you will hit the base case to return from here. Okay, perfect. So if smaller part is sorted, we get the answer from here, and if the smaller part is sorted, we are also sorted. If it's not sorted, we are not sorted. So I'm just going to return this as it is, and let's call this. Okay, I need to pass the start index, which by default should be 0. So it's saying yes, the array is sorted, and here the array is not sorted. Let's quickly see how exactly it works. Okay, so let's say you give me 1, 2, 3, 4, 5 and start index is 0. So I come here, the length is 5, start index is 0, 0 is not equal to 4, it's not equal to 5, I'm not returning true, I'm coming here. Then I compare a of si, which is a of 0, and a of 1. They are in order, they are fine. So I'm making another call, this time same array, not a copy, but the start index is 1. So I'm not going to look at this part. I'm not looking at this part. Now this function call, this was the first function call, is sorted better, where si was 0, here si is 1, is sorted better. Si is 1. So you will compare 1 and 2. They are in the order. So you're going to make another call. This time you are not going to look at these two. The start index is 2. So you will compare the elements at index 2 and index 3. So you compare these, which are 3, 4, 5. They are in order. So you're going to make another call. This time with this index, which is 3, you'll compare 4 and 5, you'll make another call with your index to be 4. Now as soon as you do this, length of your array is 5, start index is 4, that means start index equal 5 minus 1, so you will return true. This will return true, this will return true, this will return true, this will return true, and this is how the original function is going to return true as well. Right? So you made all these calls to eventually get to whether the array is sorted or not. Let's say I had a 40 here instead. So what's going to happen? So here 1 and 2 are fine, so we are going to make this call. Here 2 and 3 are fine, so we are going to make this call. Here 3 and 40 are fine, so we are going to make this call. But as soon as we make this call, the base case is not met, but this is true. A of si is 40, a of si plus 1 is 5. That means you will return false from here itself. You will not make this call if this is 1, 2, 3, 45. So you'll return false from here, this will return false from here, this will return false from here, and this will eventually return false, and you're getting the right answer. So in case the array is sorted, you're going till the end. In case it is not sorted, you will stop as soon as you find something wrong in your array or list. Okay, so that's how the whole thing is working. In the previous function that we had written, we were just making copies. We are not using the start index, we are just making copies. Okay, please solve the problems that are within the lecture flow, and in the next session we'll look at we'll start looking at a little more interesting problems within lists, and from now on we will be using this start index instead of making copies. Okay, thank you. Hi. So in this problem what you need to do is you're given a list and you need to find the first occurrence of x. What does this mean? So in case your list contains multiple places where you have x, you need to return the first occurrence. Okay, so there are two ways of doing it. First of all, let's talk about the base case. Right, the base case is my array is empty array. In that case, you don't have anything and you can just return -1. -1 signifies that you don't have x anywhere. Okay. Now, induction hypothesis is that a smaller list will tell me correctly the first index of x. Now, what do we need to do in case of induction step? So, given an list, we can check at the first place. If you have x here, then you can just return 0, assuming we are looking at the 0th place. So you can just return 0 because you have found x at the 0th place itself. Then the answer has to be 0, because even if you have x later on, you will give preference to the first occurrence of x. In case you don't have x here, then you need to find x in the rest of the list. Now we have two options. The first option is to make a copy of this list, this smaller list, and then call the same function on that. And the second option is that we will use the start index method that we saw in the last session, and we will pass a start index so that we can do the calculation, so that we don't have to make a copy of the list and we are able to use the same list. Okay, what is the difference? So obviously one difference is that using start index will be faster, it will be better. One thing that you will have to take care of, I would recommend you to write the code in both ways. First make a copy and then use the start index method as well. So while you are making a copy, one thing that you will have to take care of is, in case this smaller part returns a number k, what should you return? What do you need to return? If it's returning k, then it means x is at kth index. In the smaller part, x is at kth index. What about the bigger list? Where will x be in the bigger list if in the smaller one it is at kth index? I think you will need to return k plus 1 because there is an element at the beginning as well. So if the smaller list says that x is at k, the larger list should say that it is at k plus 1. But in case k is -1, that basically means there was no x, there is no element, no data point which is same as x. That's why it's returning -1. Then you need to return -1 because you have already checked at the 0th place. You have checked in this part as well, and there is nowhere where you have x. That basically means you need to return -1. So you have to be careful about that part. Okay, be careful about that part. And this k and k plus 1 and -1 is applicable when you are making a copy. When you are not making a copy, things will be a little easier. But I would recommend you to write code both ways. Okay, great. Please do this. Thank you. Hi. So in this session, I want to write code for finding the first index in a list. Right? Okay. So first index, you are given a list and you are given x that you need to find. Let's find the length of a, and in this particular function I'm going to make a copy. Then I'll write another function in which I'll not be making a copy of the array of the list. Instead I'll be using the start index, and I keep saying this array and list. I hope you understand we are using lists, but I keep saying array every now and then because in every other language we use arrays as the default name. Okay, so I have the length. In case the length is 0, that means the array is empty. I think I need to return -1. If array is empty, there is no way I can find x. That basically means I need to return -1. Now that you have checked that the array is not empty, it has at least one element, you can check if a of 0 equal x. Right? So I need to check the 0th element. If this itself is x, then I don't have to do anything else. I can just return 0. And if I have crossed this if, that basically means you don't have an x here, you don't have value x here, so you need to make a call on the smaller part. So let's create the smaller array by using slicing, and smaller list output you can calculate by using the same function. It's a smaller list, so induction hypothesis say that you can use the same function on this, and you need to pass x, so you get the smaller list output. So the smaller list has given you a number, I'm calling it k, here we are saying smaller list output. Now you need to check if k is equal to -1. If k is -1, that means smaller list is saying, hey, I couldn't find x anywhere. That means x is not here. X is also not here. That means x is not present in the list, and we should return -1 itself. So let's make a condition. If k is equal to if smaller list output is equal to -1, I need to return -1. Else, if it's not -1, that means you have found x somewhere. Let's say we found the x at location 3, index 3. The index 3 is specific to the smaller list. It's with respect to the smaller list. That means you need to return this +1, because you have another element in front which you have not accounted for, so you need to account for that as well, and the index in the total list becomes smaller list output +1. Okay, before we run this, let's see how this is working. So let's say this is my input and I'm searching for 7. Okay, I'll take two examples, in one in which you have 7, in one which you don't have 7. Let me put another 7 here. Let's say this is my array. Okay, so I need to find 7 here. Perfect. What is the length? Length is 7. Okay, let me take another example. I don't want the length to be 7. Let the length is 8. Okay, too many 7s will become confusing. So you have 8 elements. 8 is not 0, so you come here. This is not 7, so you come here. You make another list, smaller list, which is a copy 3, 5, 7, 9, 7, 10, 11, and you call the same function on this. So you want to find 7 in this one. You again go there, the length is still not 0, the 0th element is still not 7, so you make another copy and you ask it to find 7. Length is still not 0, you don't have 7 here yet, so you basically make another copy and you ask it to find 7. Length is not 0 yet, but you have a 7 at the beginning. So this list is going to return, hey, I have found 7 at 0 index itself. Now this list here, this function here will say, hey, you haven't returned -1, that means you found something, and because you found something, I'm going to add +1 in it, so it's returning 1. That means it's saying, hey, I have 7 at index 1, which is correct. Then this is going to say, hey, I have 7 at index 2, and this is going to say, hey, I have 7 at index 3, and it works fine. Let's take another example. Let's find 7 in this. So length is not 0, 0th element is not 7, so we make a copy, we call here, again length is not 0, 0th element is not 7, so we make a copy and we try to find 7 in this. Length is not 0, 0th element is not 7, so you make another call, length is not 0, first element is not 7, you make another call, 11, 7. Length is not 0, it's still 1, the 0th element is not 7, so you make another call, to an empty list. As soon as you reach an empty list, you return -1. So this returns -1. Now this list here says, oh, my small list output is -1, so I need to return -1 as well. This will say, hey, I got -1, so you're going to get a -1 as well. You're going to get a -1 as well. You're going to get a -1 as well. And you're going to get a -1 as well. And my function will return -1, which is the correct output. Okay, which is the correct output. Perfect. So let's print first index of 7. First index is not defined. We didn't run this cell. Let's run this now. It's saying 5, which is correct. 0, 1, 2, 3, 4, 5. Index 5 is where 7 is. Okay, so it's working fine. So let me quickly make a copy of this, and this time I'm not going to make, okay, let's not make a copy. Let's write the function again. And we don't want to make a copy of the list given to us. We don't want to do this. We want to use the same list by using start index. Okay. First index better, A, X, and start index. Okay. Let me find the length. Now you have this list and you're given a start index. What should be the base case? The base case will be when I don't have anything to do work with. There is no elements left. That means my start index is here. That means start index equal length. So if it is equal to L-1, that means there is only one element left. If it is equal to L, that means you have crossed. There is nothing left. Okay, so my base case is SI equal L. That basically means the start index is pointing towards no element. There is nothing left. I can't do any more work. So that means I can't find X anywhere. That means I'm going to return -1. That's the same as this one, but this time because the list is not reducing in size, list L is not going to go to 0, but the start index is going to go towards L. Okay, so if that means I can return -1. Okay, what to do now? Okay, so this is my array. This is the start index, and there are some elements left. Because if there was no element left, I would have returned -1 from here itself. So now I need to check at the first element, the 0th element, which is not at 0, which is at SI. So I'm going to check if A of SI equal X. In this case, I'm going to return. Now I'm not going to return 0. There is no point returning 0. Now I know this is a bigger list, and I know the exact index where I have found X. So I am going to return SI itself because I have found X at SI. Now let's call the smaller. We don't have to create the smaller list. We just need to call on this list itself first index better. The same list, same X, but SI will be increased by 1 because this is the case when you could not find X at SI. We don't have X here. So we are making a call on this part. Okay, we're making a call on the smaller part. Now, whatever the smaller part returns, if it returns -1, I want to return -1. If it says that, hey, I have it index 9, then the index 9 is not in the smaller part, it's in the actual list. So I can just return that as it is. Okay, I can return it as it is. Let's take an example. So let's find 7 in this. So what's going to happen? Start index will be 0. You will say, I don't have a 7 here, so we'll call start index 1, not 7 here. Start index 2, we don't have a 7 here. Start index 3. With start index 3, you will find 7 there and you will return 3. So you will get a 3 from here. Now you don't want to add 1 into it because in the original list you have 7 at index 3. So you don't have to do +1 the way we were doing it here. Okay? Because we are not making a copy. So you get the smaller list output, and guess what? You don't have to do anything. You can just return the same. And let's see if both these return the same value. First index better, a comma 7 comma 0, which is the start index, and yes, both of them returning the same thing. You have seen the solution, but please write this code by yourself, because unless you do that, you will not really understand how things are working. Okay, thank you.
So in this session, we want to look at an extension of the previous problem that we have seen. So instead of finding the first index, we want to find the last index. So you're given a list. In this list, you want to find the last occurrence of x. That means if you have x here, and x here, you don't want to find the index of this x, you want to find the index of last x. Okay, so in the previous session, we saw how to find the index of the first occurrence of x. So that's what we need to do. Now, one easy way of doing this is that in the previous session, we started looking from here. We were looking if x is here, then we are making a smaller list, and then we are going in this way. The easiest solution will be that you look at the last element. If the last element is x, you return the index of last element. Otherwise, you start shortening your list from this direction. So instead of saying this, you will be saying this. So my list will be getting smaller from the last element. But I don't want to do that, right? That's not the purpose of this particular problem. What I want you to do is shorten the list from the beginning only. Okay? So what were we doing last time? In finding the first index, we were trying to check if you have x here. In case you have x here, you will just returning the index of this particular place. Now it was 0 in case you were trying to break the, like calling smaller list, or it could just be the start index, right? It's possible it's the start index. Any case, you were looking if the first element is x. If it is x, you were not looking in rest of it and you were just returning. You can't do that now, because even if you have x here, you need to keep looking, because if there is an x later, you need to give preference to the later one. In the previous problem, we had to give the preference to the first one. Here we have to give a preference to the later one. So even if you have x here, you can't stop. You need to check if you have x here. And if there is one, then you need to return that last index and not this one. Okay? So let me repeat it again. What I'm proposing is, for now, let's not worry about start index or whether we are making the list smaller or whatever we are doing. Let's just focus on the problem. Okay? Let's not worry about how exactly we are going to implement it. Let's just focus on the problem for now. So, because in the previous problem we had preference to the first element, we were checking the first element first and then calling on rest of the list. In this problem, let's call on rest of the list first. If this returns a -1, that means you don't have x in this part of the list. Only then I will check here. Because in case rest of the list says, here I have an x at index 5. Why do I even care if there is an x here? I don't have to check if there is an x here. I'm only going to check if there is an x here if I get a -1 from rest of it. Because if there is already an x here, I don't care about this anymore. Okay? Base case, exactly same. If length is 0, we can return -1. Hypothesis, the smaller list will return the correct last index of x. Step, first call search or last index on smaller list. If small output is -1, only then check the starting element. So we'll first call on this. If this returns -1, only then we will check here. Otherwise, we'll return whatever is the output from here, we will return that. Now, I would recommend you to write this code both ways. First of all, making smaller list, then using the start index method that we used earlier. Okay, do it both ways, and then I think you will get a lot of clarity on how exactly to use recursion with arrays. Okay, thank you. Hi. So in this session, I want to write code for the last index problem. Okay. So we have already seen how we are going to write code for this. So let's quickly jump to code. I'm just going to brief you again. So first of all, the base case will be if length is 0, I'm going to return -1. And to start with, I'm writing code for copying the smaller part. I'm not using start index. I'm going to copy the smaller part and I'm going to use that. Okay, so if length is 0, I'm going to return -1. If length is not 0, in case the length is not 0, then I'm going to call on the smaller part first. Because if there is an x here, I will give preference to that rather than if there is an x here. Okay, so I'm going to first call on the smaller part. If that returns -1, then I'm going to check on the starting element. Okay, so let's quickly write code for this. Okay, last index, my list and my element x. Okay, so let's get the length of a. In case length is 0, you can return -1 because there is no element present in empty size list, so you can just return -1. Okay, so if I'm done with this and I've reached this place, that means my list has at least one element. Okay, now we'll first create the smaller list, check on the smaller list, now the smaller list has given its output. So this has given the output. In case this returns a -1, I will have to check here. In case this returns a 3, what does that mean? That means that you have x at index 3 in the smaller list. So you need to add +1 corresponding to this element. Okay, so you'll have to add +1 corresponding to the element that you have removed. So if smaller list output is not equal to -1, then I'm going to return smaller list output +1. Else, what does else means? Else means it is -1. If it is -1, that means it's not in the smaller part. So I need to check if a of 0 is equal to x. If you have x at the 0th element, now you don't have x anywhere else. So if you have x at the 0th element, then you need to return 0. Because that's the first as well as the last index of x. And in case you don't have x here as well, in case you don't have x here as well, then you return -1. Okay, in that case you can return -1. Let me create a list. Okay, x is 4. Let's return the last index of comma x. Okay, seems like we did something wrong. Seems like recursion depth exceeded. So there is something wrong which is going on. Let's just see what happened here. Oh. Okay, so seems like the error is that we are using A here. We are calling last index on A. We had to call it on smaller list. We have to be careful about what we are doing, right? So now you get index 7 as your answer. So let's see. Index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So yes, this was the last index where 4 was present. Seems like this is working fine. Right? So let's see how it worked. So let me take a smaller example for our dry run. Okay, so I'm going to take this example, and this should return 0, 1, 2, 3. Okay, so it's returning 3. So you have 1, 4, 5, 4, 8, and you're looking for 4. So as soon as you come here, you check the length is not 0 for sure. So you make a smaller list and you call 4 on this. The length is not 0. There is 4 at index 0. No, you don't worry about that. You are not checking A0 being x till later. So we are not going to check for this element. We are going to call on 548. Looking for 4. It's not going to check if 4 is present here. It's going to call on 4, 8 with a 4. Now you have a 4 here, but it's not going to look at that. It's going to make another call at here. Then this is going to make another call to empty array and 4. Now empty array will say, hey, the length is 0. I'm going to return -1. So it returned -1. So you got -1, right? So you went here. You checked if A0 is x, but it's not 4. So you continue returning -1. So this function got -1. So this also came here. Now it's checking if A0 is 4, which is 4. So you return 0 and you don't return -1. So you're returning 0 from here. This function gets something which is not -1. So it adds 1 and returns it. It returns 1, this returns 2, this returns 3, and that is the correct answer that you were looking for. Okay? So the difference between finding the first index and last index is there we were looking at the 0th element first and making rest of the call. Here we are making the call first, and whatever the answer is, depending upon that we are deciding if we need to check for the 0th element or not. Okay, that's how this function is working. Perfect. Now I'm going to code it again, and this time we are not going to make a copy. And by now I'm hoping we are really good at doing this, so I'm going to be a little fast. So last index better, we get the list, we get the x, length is equals to L is equals to length of A, and we also get the start index. Right? We get the start index as well. So now if start index is equal to L, that means you have nothing left. There is no element left. So you can return -1. Right? You can return -1. We don't have to create the smaller list. So we will directly call smaller list output. So we are planning to check for the 0th element later. We are not checking right now. Last index B you'll pass a, x, and si plus 1. Si plus 1. Okay. Now the code will be very simple. If smaller list output is not equal to minus 1, that means so my list I called here, and this one is saying, hey, I have found something. But this time I'm not going to add a plus 1 to this, because it's going to return the actual index in the complete list, not just this part. So I'm not going to add minus 1. In this case, I'm going to return smaller list output, else, wow, I have received minus 1. That means you couldn't find x anywhere here, right? Okay, let me just do this again. So this means I got a call here. I have called on this part. I couldn't find x anywhere here. So now I am going to check at this particular index. So if we are getting minus 1, so there is no x here. If there is no x here, you need to check at the si element as well. So if a of si equal x, you return si, else you return. You didn't find it in the smaller part, you didn't find it in the beginning element, you didn't find anywhere, you return minus 1. Right? You return minus 1. I think this should work. Let's print this. Let's also print last index better. A comma x comma 0. And this works fine as well. Okay? Let me dry run this for you. The second one. You have this. This is your list. Your element that you are looking for is 4. Start index is 0. As soon as you come here, start index is not equal to the length. So you make another call, and this time you're looking for 4, you pass it 1. Again you are passing the same array, but you are saying start index 2. Still the start index is not equal to length, so you make another call. The same list is getting passed. 3. You make another call. Still the start index is not equal to it, so you make another call. Length is 5 and start index is 4. This time the si start index is equal to length, so you return minus 1. So you return minus 1 here. Now what does this function say? This function says, okay, I have received minus 1, so I need to check if a of si is x. Si is this. Si was this was the si, this was the si, and this was the si. So you check si here, and you see that you have an 8 here, you don't have 4 here. So you return minus 1 from here. Once you return minus 1 from here, now this call also looks at si, which is 3, which is this index, and it says, oh, I found 4. So it's going to return whatever index you had. So it's returning 3. So this one got not equal to 0, not equal to minus 1. So whatever you returned, it's going to return the same thing, and same thing, which is the correct answer. There is a slight difference between both the function. This function returns the index as per the smaller list that you have passed. This function returns as per the index in the complete list, and not just the smaller part, right? In the complete one. So if you have 4 here, this will return 0, this will not return 0, this will return si, right? And we are handling both the conditions accordingly depending upon the function. Okay, so great. So we have written a lot of code by now. Please work on the assignment, and in the next lecture we'll start looking at a lot more interesting problems to gain a lot more confidence on recursion. Okay, thank you.